So over the last couple of weeks, we studied optimal control theories, okay? Variational approach, dynamic programming, ECMS, and so forth, right? But at the end of the day, what we want to do is we want to apply these theories for hybrid electric vehicle control problem, right? And this is that lecture. We're gonna first start with applying dynamic programming to parallel hybrid electric vehicle, okay? By the way, the midterm exam coverage is going to be up to this lecture, okay? Or homework number 3, okay? By the way, do you guys, how are you guys doing with homework number parallel hybrids, okay? So this is the target vehicle. This is a P2 hybrid. Motor is located before transmission, between engine and transmission, okay? And these are vehicle specifications, and I believe we handed out the model, right, for homework number 2. Which is this model, right? So we have driver model for velocity tracking, and we have vehicle dynamics, battery dynamics, and we have transmission, engine, and motor generator model, but those are mostly lookup table, efficiency map, okay? And then we have controller, right? And our task is to design this controller, or let DP find the optimal solution, right, to determine these control variables. And then hopefully we can design controller based on the DP solution, okay? And this is DP problem formulation, okay? So obviously we want to minimize fuel consumption, right? So we have this cost function that minimizes fuel consumption, but we have these other terms such as gear shifts and engine on off. So this is added because DP doesn't have any idea about, frequent engine on off or frequent gear shift. So we need to add the term so that DP can handle these things, right? So, and then we have SOC constraint. By the way, this problem was for plug-in hybrids. So, for example, this is HEV problem, and this is plug-in hybrid problem, where X is either distance or time, and then Y being SOC. So for plug-in hybrid, this is the constraint, but for hybrid, you need to meet that constraint, right? Depending on the problem. And control inputs are gear, which gear we are going to use, and then engine torque. How about motor torque? We need to have this. How about motor torque? Well, it's called a drivability constraint. So, which should be included as a part of constraint, which is if you think about it, the engine power is coming and battery motor power is coming in, right? So if you have power demand, then summation of these two must be equal to that, right? Otherwise, driver can request for 50 kilowatts, but if you are outputting 30 kilowatts, then it's not a good vehicle, right? It's not a good product. You're not meeting the drivability, right? So that's a very important constraint. So if you use that constraint, then you can remove one freedom for motor torque. Because if you know this and this, then this will be automatically determined, right? Any questions? Everybody good? What about states? Well, there's SOC and vehicle speed, but vehicle speed is also constrained by the driving cycle. And that determines power demand. Vehicle driving cycle determines power demand cycle, power demand trajectory. Okay, so power demand is given by the vehicle speed, driving cycle. And then we only have to now determine either engine power or motor power. And in this problem formulation, we chose engine power as the free control input. But motor power is automatically determined. Okay. So vehicle speed and power demand are constrained by driving cycle. Okay. So now this is the solution. So I'm not going to talk about how to implement DP, but you will, I think you will have a little bit of flavor of that in a lab. By the way, we have a lab session tomorrow, okay? Tomorrow, 10 a.m. And you guys will learn how to code ECMS, which is similar to, other optimization codes, how to optimize, how to find the optimal solution for HEV problem, okay? Anyway, so assuming you develop the code and you run the code, and this is the solution. Okay. And now you are looking at torque and gear inputs. These are control inputs. This is your state. This is speed, engine speed, and transmission input speed. And then vehicle speed and fuel consumption rates. And then PSR, power split ratio. So PSR is defined as engine power divided by power demand. Okay. So if PSR is 1, then it means engine driving mode, engine only mode. Okay. If PSR is smaller than 1, then it's power assist. Motor is assisting. If PSR is larger than 1, then it's a recharge mode. Then you are charging the battery. Okay. So the solution looks something like this. And this is zoom in plot from 0 to 250, something like here. Okay. So if you take a look, so you're looking at transmission input speed, right? So which is directly related to vehicle speed with gear ratio. But engine is sometimes disconnected when you are doing regen or EV mode. But when engine is on, they're equal, right? This is regen, this is the EV mode, this is hybrid mode, okay? And then you can see that during hybrid mode, so during EV mode and regen, motor torque equals total torque, which is transmission input torque, because the engine is disconnected and drivability constraint has to be met. But when it's hybrid mode, you have combination of motor and engine. So you have a motor, you have engine, and blue one is combination of that, right? So if motor is negative, then it's charging. If motor is positive, then it's assisting, okay? But this is just trajectory, right? You're looking at time response. But we need to design controller, right? How do we design controller? Well, and this doesn't tell us anything about strategy, control strategy, or what DP is doing from strategy perspective. So to analyze that, we can do further analysis such as these. So we are plotting operating points on vehicle speed versus power demands, and vehicle speed versus traction force or wheel torque. And you're looking at two plots here. Let's take a look at the right one. The red dots are engine on points. Blue dots are engine off points, so EV modes. Okay. And if you look, there's clear cut between the EV mode and hybrid mode, right? So this is HEV mode, and this is EV mode. This is so much helpful, right? Then time response. Because this we can learn something from this, and we can derive strategy from this. For example, when vehicle speed and wheel torque is here, then we should turn the engine on. Or if vehicle speed is low and wheel torque is low, then we can operate in EV mode. This is a direct output of DP, okay? I didn't do anything. Raw data. Oh, by the way, this is the result of my PhD work. So you're looking at my PhD thesis work. And if you look at this left plot, you can see how shift strategy should be designed. So again, X is vehicle speed and Y is power demand. And I'm plotting operating points based on the gear selection. And you can also see separation between different regions. Can you guys see? Again, raw data from DP. Isn't this nice? This tells us so much about how optimal strategy should be. So now this is related to transmission control, and this is related to engine and clutch control. Any questions? Well, I have one more results plot, which is power split ratio. So this is one of the key parts, and actually, so we talked about engine on-off strategy and then shift strategy, but the key part is how to blend engine and motor, right? So in other words, if we have power demands, how much should be engine power and how much should be motor power? Because when this is 100 kilowatts, we could have 70, 30, 50, 50 or 30, 70, right? How to blend is a key. And if you look at this plot, it gives us some idea, okay? So I drew lots of plots and found out that there's a relationship between power split ratio and input torque, transmission input torque. So when transmission input torque is large, PSR tends to be low. When transmission input torque is high, then PSR tends to be high. So can you guys see that that relationship? So this is T I, could be demand or just TI. And this is T motor, T engine. So TI is just summation of TE and TM because everything is rotating at the same speed, right? So this is just power demand requirements, right? This one. And can you guys see why DP is doing this? Can you interpret this result? I mean, it's not that complicated if you think about it. In fact, it's somewhat. 승택 학생 뭐 얘기했었나요?
제가 이름을 잘못 등록한 것 같습니다.
네?
이름을 등록을 잘못했습니다. 노트북을 빌려가지고.
아, 미안해요. 이름이 뭐였죠?
김병준입니다.
아, 병준 학생. 병준 학생 뭐 무슨 얘기했던 것 같은데.
아, 이게
딴 사람하고 얘기했나요?
아니 이게 그 DP가 어떻게 작동하는지를 물으셨는데 그 그래프가 오른쪽 위에 있는 그래프인지 잘 몰라가지고 혹시 그게 맞나요?
그러니까 지금 요 그래프를 가지고 이제 얘기를 했었는데요. 토크 디맨드가 클 때는, 그러니까 인풋 토크가 클 때는 PSR이 낮아지고 인풋 토크가 낮을 때는 PSR이 높아졌다는 어떤 경향성이 DP에서 나왔는데 이게 물리적으로 무슨 의미일까요? 그리고 왜 그럴까요? Well, if you think about it, when high torque is necessary, then it would be nice to assist the engine. And that's what's going on here. Rather than operating the engine at inefficient region, which is this region. Right? So engine is efficient in this region or in this line. And if torque demand is low, then it's a good idea to recharge the battery. Because if you operate your engine at low power, low torque, then it's not efficient. So it's a good idea to operate your engine in this efficient region and motor take care of the rest. Meaning that if you have a lot of power, then you reserve that energy. And if you don't have enough power, then motor supports, assist. Okay, so that's what's going on here. Okay, so if you actually see this plot, this is engine operating points. And you can see it's actually operating quite in the efficient region, but there are still some inefficient points. But this is because we only have four speed. So for high speed, you don't have choice. You have to operate here. Okay. And so based on these learning findings, what we want to do is actually design rule-based controller that's near optimal, right? So we have, because we can directly implement dynamic programming, because the direct output of dynamic programming is time-varying policy, time-varying control policy, meaning that it's a function of K, because we were solving deterministic dynamic programming, and we were using drive cycle, meaning that for given speed, we were looking for U star. And dp, what dp is giving us is U star that's function of both x and k. Remember, stage, so time, and x. So dp solution is function of x and t, or stage. And that's exactly what this is, right? So U star, okay? But because this is function of k, we can't use it as a controller, real-time controller. Because in real world, driving cycle is not fixed. Driving cycle can be anything, right? So this optimal policy was optimal policy for the given driving cycle. And even at given instant. So we need to somehow learn policy from the trajectory, or that's exactly what we did here and here. So we were trying to learn strategy rather than trajectory or U star, okay? So we plotted how DP operates on these different different planes, okay? And from these plots, we can actually extract strategy. And that's what this figure is showing. So we extract strategy, and we improve or design rule-based controller that's near optimal. Then now this is systematic design approach, right? Rather than tuning and calibration. Remember, DP is not directly implementable, okay? And then we talked about the target vehicle. We talked about Simulink model. And then we talked about DP problem formulation, which consists of cost function, constraints, control variable, state variable, and constraints. And then we looked at DP solution and see how DP behaves over time in time response. And then we wanted to see how DP behaves in a strategic manner, meaning that rather than time response, how does DP controls transmission, motor, and engine, something we can actually interpret. So this was some of the analysis results. So we looked at shift strategy, and then we looked at engine on-off strategy, where engine on-off has a clear separation between some constant power line. And then we also looked at shift strategy, where some clear separation can be observed. So this is something, engineers or human can actually explain, right, as a logic compared to time responses. And then we also looked at power split ratio, which is engine power divided by total power. And we looked at there is power assist, recharge mode and power assist mode, and then engine only mode. So when torque demand or transmission input torque input total torque is high, then it's a good way to assist using the motor. And if the torque demand is low, then it's efficient to recharge the extra torque and power from the engine. But remember that input torque is strongly dependent on transmission gear. Because if gear ratio changes, torque input changes for the same power demand or power output, right? Because this is T omega. So you just need to be careful with this, okay? This x-axis is torque input, torque at the transmission input. And this is highly dependent on gear ratio, okay? Meaning that if you select different gear, your torque can change substantially. So this is coupled, okay? But this engine on-off was almost constant power line, right? So if we are using power as a threshold, then it's not dependent on the gear ratio, okay? Because we're talking power. How about here? Vehicle speed and power. Well, again, y-axis is power. So it's independent from the gear ratio. Okay. So in summary, the PSR is the only strategy that's highly dependent on the transmission gear. Okay. Remember, this is power blending. This is gear ratio. This one is engine on-off strategy. Okay. So those are three key decisions we have to make, or energy management strategy must make. Okay. And so we did this analysis, and how can we utilize some of these information and knowledge to design energy management controller? Well, obviously we can improve it based on these strategies or analysis results we obtained. Okay. And this figure explains how we can do it. So we have a driving cycle, model, target vehicle, everything ready, and then we apply DP. We obtain optimal control policy, and then we can analyze that, and then improve rule-based controller. Why not apply use start directly? Anyone?
Isn't it because U star is only optimized for a specific driving cycle and a specific, so basically it's very limited.
I can't hear you.
Sorry. Isn't it because the U star is basically very limited to the specific condition?
Is it just me?
And the what?
I can't hear Neil. Everybody can hear Neil?
My system is working.
Oh. Something wrong with my computer, I guess. 잠깐 나갔다 들어와 볼게요. DP outputs U star, that's function of state and K, where velocity and power demand is predetermined for each K. So this is no longer, this is time varying controller. Okay. So this is optimal for that K, where K has power and velocity fixed. So we can directly use that, use this U star. Okay. So we had to extract a strategy from it in a language we can understand, and that's what we did here. Okay. And then there is also a lot of good features about the rule-based controller. If you use rule-based controller, it's very intuitive, logical, and we can debug much easier compared to just directly using, output of DP or something like that, or a lookup table. So it's usually more robust. Okay. And this is this was what I proposed in my work, in my thesis. So this is somewhere between rule-based controller and DP-based controller, or DP-based SPC, and SPC stands for supervisory powertrain controller, but it's often called hybrid control unit, or energy management controller. There are just different names for it. Okay. Anyway, so in the architecturally, you can see that it's a logic. This is a flow chart. Okay. But we also wanted to achieve near optimal fuel economy, right? So how can we do that? And the approach was this slide. So came up with this logic where some of the key decisions can be made from DP results, meaning that we can extract some of the key strategy from DP results. So let's go through this. Okay. So we first start here, and we see if power demand is positive, then we are going to driving mode. If it's negative, then go to region mode. And for driving mode, check if power demand is larger than or lower than the threshold value, engine on-off threshold power. So if engine on-off threshold power is larger than some value, then engine is on. If it's smaller, then it goes to engine off mode, and now it's basically EV mode, right? And then once you come to EV mode or regen mode, you need to determine which gear you are going to use, and then do the regen or EV driving. But for regen case, if vehicle speed is smaller than 60 km/h, then we're going to disconnect the engine. If it's if it's higher, then we're going to do engine drag, because at high speed, engine disconnect and reconnect can be can hurt the drivability. Anyway, so EV is relatively simple. EV path is relatively simple to optimize, okay? Because you only have one power source, motor. But in the case of hybrid mode, things become more complicated, okay? So now you're now entering engine on mode, which means hybrid mode. In that case, you need to first determine gear ratio. And gear ratio will be function of vehicle speed and power demand primarily. I'll talk about theta later, okay? And then once you select a gear, you can compute input torque demand, transmission input torque demand, and transmission input speed, okay? Everybody follow? And then we can compute how to blend between motor and the engine. So using the power split ratio map. So if PSR is larger than 1, then you're going into recharge mode. If it's lower than 1, then it's assist mode. If it's 1, then it's engine only mode. Okay. Any questions? Any questions? No? Is that straightforward? So what's going on here is we can pretty much determine, so everything is pretty much just logic, simple logic, right? If this is the case, then do this. If that, then do that, right? Except for this part, right? So here, what should be the threshold power? Here, what should be this map, right? And then this is the power split ratio map. So we can use these three strategies we extracted from DP inside of this rule-based controller. Okay. So we are still using rule-based controller, but then the key decisions can be learned from DP. Okay. You can also think of this as a learning, not just deep learning is learning, but DP is solving the optimal control problem, and then we go through some post-processing so that we can implement this in rule-based controller, and engineers, human, can also understand what's going on, something that's interpretable, right? What's the benefit? What's the advantage of doing this? Because we have to go through the post-processing. 경준 학생? 답변해 줄 수 있을까요? 이렇게 DP를 분석해서 뭐 일종의 포스트 프로세싱 작업을 통해서 이렇게 익스트랙트를 해서 활용을 하는 거의 필요성과 장점이 뭐가 있을까요?
일단 한눈에 보기 편한 것 같아서 중간에 바꾸고 싶은 부분만 따로 골라서 바꿀 수 있다는 장점이 있는 것 같습니다.
지금 스피커가 아직 좀 잘 안 들려가지고 오늘은 그냥 진행을 해야 되겠네요. 이렇게 함으로써 어떤 장점들이 있을까요? 일단 방금 전에 말씀드렸던 것처럼 이런 굉장히 좀 로버스트하고 릴라이블하고 직관적인 로직들 형태로 우리가 쓸 수 있죠. 이제 그죠? 이런 룰 기반의 제어기를 큰 틀에서 우리가 쓸 수 있게끔 가능하게 해줬고, 그죠? 그 다음에 어떤 그 엔지니어나 디자이너가 이해할 수 있는 이런 이제 그 전략을 도출을 하고 그 전략을 필요하면 필요에 따라서 우리가 수정을 할 수가 있겠죠. So I was telling students that by going through the post-processing and extracting strategy from DP, we can actually use the rule-based controller, which is very robust, reliable, and logical, and computationally light. And we can also use explainable or interpretable strategy for the key parts. So engine on-off decision, gear selection decision, and then power blending decision. So all of this is from DP. So this is explainable or interpretable. At the same time, it's near optimal, right? So those are the benefits, and we can also modify or tune these strategies because it's interpretable, it's explainable. And then let's move on to the next page, which is comparing performance, simulation, fuel economy performance, comparing DP, and then this is ECMS, or instantaneous optimization, assuming we know the equivalent vector, meaning that we know the future information. And then this was the proposed algorithm, which is DP-based controller. And you can see it's better than instantaneous optimization and quite close to DP. Okay. And these are the time response of DP-based controller comparing with DP, and you can see they're quite similar. Okay. And let's move on to parallel hybrid. So previously we looked at hybrid electric vehicle energy management problem, but now here we are going to look at plug-in hybrid electric vehicle problem, which is similar but somewhat different. Why is that? As to sustain charge, right? Initial and final SOC must be equal to the same, right? But plug-in hybrid mainly uses battery as main power source, and you can deplete the battery. So it starts from 100% or 90%, and then you use that battery energy to drive the vehicle, and at the end of the cycle, at the end of the trip, you just need to make sure SOC is above 20% or something like that. And then you need to, switch to hybrid mode, charge sustaining mode. But what would happen if you let DP solve the problem? Meaning that give 20 or 30 miles of trip and then start from 0.9 SOC, and constraint is SOC has to be higher than 0.2, then what's going to happen? So the cost function and control state space constraints are very similar, all the same, except for this SOC constraint. Okay. Then we expect the trajectory looks something like this, right? But you never know, right? It could be something like this, It could be something like this, right? You never know. So I solved it, okay? So I solved it for two trip distances, 20 and 30-mile trips, because the target vehicle had all electric range of 20 miles, meaning that the battery can provide EV power up to 20 miles. So up to 20 miles, the optimal solution is trivial, EV mode. 그러니까 플러그인 하이브리드 같은 경우에는 20마일까지는 EV 모드로 달릴 수 있을 만큼의 에너지가 있죠. 그러면 20마일까지는 퓨얼을 안 쓰는 옵티멀 솔루션은 그냥 EV로 달리는 거겠죠. 그래서 트리비얼 솔루션이 나오는 거죠. So we wanted to see the two different cases. So one is 20-mile case where the solution is somewhat trivial. Just use motor and battery as much as possible, then you will minimize fuel consumption. But if trip distance increases higher than 20 miles, then you have to use engine. But when and how is the question, right? And DP has to find that out. By the way, for this optimization problem, the motor and battery power is set to about 60 kilowatts. For hybrid, it was about 30, 35, okay? So now we have bigger motor, bigger battery, okay? And here we use LA92 cycle because we wanted to make sure that if driving cycle or power demand is higher than the motor and battery power, then engine has to come on, even if battery has enough energy, okay? So we wanted to see if that actually happens, okay? So here we go. So 20 mile and 30 mile. So this is gear and then throttle, and then you're looking at power, fuel consumption rate, vehicle speed divided by 20. And then the black dots are engine on points. And this is the SOC. And notice that engine still does come on because we use driving cycle that's aggressive so that it requires high power. And if motor power cannot provide that power, then engine has to come on. Okay. So even if battery energy is full, okay. And let's look at 30-mile case. Now you can see that engine on points are more observed, right? And more fuel consumptions, right? Which was expected, right? Because we have to travel longer distance. So just there's not enough energy from the battery to drive 30 miles. The battery can only provide 20 miles. And then we need to somehow learn how we need to control plug-in hybrids, okay? So we so far we talked about non-plug-in hybrids, right? There's conventional hybrids. And then we proposed, rule-based controller, and then we can extract some of the key strategies from DP. And we need to do the same for plug-in hybrids. But how, right? How do we analyze and extract information from DP? And how can we design the logic, the energy management strategy, control logic, so that we can use the DP extracted strategy, okay? So accommodate DP analysis results, okay? Well, we can first observe one thing here. So if you look at the SOC trajectory, you can see they're almost linear, right? It doesn't behave like this, right? And by principle of optimality, we can say that this the U star that's on this line are the same strategy. Or let me rephrase that again. So in other words, if we start from here, then it'll go through this solution. Or if we start from here, then it'll go through this solution. If we start here, then this is the solution, right? And if you actually look at other solutions, then you can see the same behavior. So if you pick a point, then this is the trajectory. If you select this point, then this is the trajectory. And you can see how SOC trajectory behaves over the distance, right? And what this means is that we can look at each solution as a group, as the same strategy, similar strategy. And if we can use this theta value, then we can somehow predict or tell the controller how to control, meaning that so let's talk about this a little differently. So this is distance. This is how much I have to travel in the future. So this is energy required, right? Y-axis is SOC. This is how much energy I have now, right? So if you pick a point, then if you draw a line, and this angle called theta is the ratio between the future distance and the SOC. Okay, so the assumption is remaining distance is known. Then I'm going to define energy to distance ratio. Okay. So this is energy, this is distance. And theta is, or tangent theta is delta SOC divided by remaining distance, right? By geometry. And then if you inverse tangent, then you get this equation. And then for small angle theorem, so if theta is small enough, then this is true. And we might want to normalize things. So we can actually find the maximum theta, which is associated trajectory for EV mode. So fastest depletion trajectory. Okay. So you cannot deplete your battery any faster than this, right? So this is maximum. And if we divide it by maximum value, then theta bar, normalized EDR, is now 0 to 1. So this becomes 0, which is hybrid mode, non-plug-in, charge sustaining. And 1 becomes EV mode. Are you guys following? Any questions so far? Is this interesting concept? So this was the key part of my thesis. So how to, and then I can also manage energy more wisely, right? More efficiently. So I move on. So now let's move on to the extraction part. So now for non-plug-in case, what we were doing was starting from 0.6, and then we get the trajectory, and then we analyzed, right? But what we are doing here is that we think that dp should behave differently for different theta values, right? Obviously, right? EV, EV, EV strategy should be different from hybrid charge sustaining strategy, right? These two should have different strategy, right? So starting from that concept, what we need to do now is we need to extract strategy for different theta values, okay? So now we are going to change theta. So this was the optimal control policy we are given for all K, for all SOC, right? But now what we want to analyze or find is engine on-off strategy as a function of theta, shift strategy as a function of theta, and power split ratio strategy as a function of theta. How would you do it? Well, we can group optimal control policy, or we can extract different strategies from one policy. Okay, so we can group things like this. Okay, can you guys see what's going on? So we are going to change theta from 0 to 1, okay? And then do the same analysis we did in hybrid electric vehicle, non-plug-in case, and see what happens, okay? Here's the results. So you're looking at 4 results. One is theta equal to close to 0, and theta equal to 1, close to 1. Then theta equal to 0.35, theta bar equal to 0.6. So EV to non-plug-in CS mode, and then 2 different levels of depletion mode, okay? And let's look at what's going on here. So again, this is EV and this is CS, or just HEV. And if you look at this CS strategy first, this looks familiar, right? This is similar to the strategy we saw earlier. Right? But what about EV? Well, all the points are EV points, engine off, except for high power case. Well, in this case, engine is coming on because motor and battery cannot provide that power. This is 60 kilowatts. So if you need more power than that, then engine has to come on. What about the between, somewhere between those two extreme cases, between ES and EV? You have CD, charge depleting mode. And you can see the threshold value, threshold power now starts to go up, right? Can you guys see? That means more EV mode is operated, right? Or engine should be turned on at higher power demand, right? If you think about it, it's obvious, right? And DP is just telling us that result. Again, this is DP results grouped by these 3 strategies for different data values. Okay. Let's move on to shift strategy. Oh, by the way, so summary of this is engine on-off power threshold should be adjusted as a function of theta bar. This is CS, hybrid mode. This is EV mode. Okay. So depending on the remaining distance and SOC, available SOC, you can compute a theta bar, and then you can change engine on-off power threshold. So you need to adapt to it. What about the shift? Well, similarly, let's start with charge sustaining in EV. Well, again, for charge sustaining, this looks quite similar to what we saw before, right? For the hybrid analysis, right? Something like that. What about EV mode? Well, there is just not enough operating points. We just have these points. Why? Because engine doesn't come on. So we just don't have enough hybrid mode engine on points or shift points for EV case, or theta bar equal to 1 case. What about the between 2 cases? Well, let's look at theta bar equal to 0.35. We can also draw some line here, right? And we can also do the same for theta bar equal to 0.6. And it's I mean, it's arguable, but I think that the shift strategy is getting more upright. But we can't really, you know, show that because we don't have many points for EV case. But you can see that these points are shifting. The lines are shifting. And more upright shift line means early shift. This is early shift. In fact, if you shift early, then what's going to happen? shift를 빨리 하면 어떻게 될까요? If you shift early, then you're going to need higher torque at the transmission input. If you shift early, your input speed, transmission input speed drops. And to provide the same power, your torque has to be larger. And what happens at high torque at the transmission input? Well, it's in this region. Then it's more motor assist, right? So let's summarize that again. So if you have more battery, then you have larger theta bar. And in those cases, you shift early. And by shifting early, you're going to need higher torque at the input. That means you're going to use more motor and battery, which makes sense, right? So these recharge mode is only available when theta bar equals to 0, when theta bar is low, right? Because you have to sustain charge. Anyway, so one of the key summary here is that engine on-off strategy needs to be adjusted as a function of theta bar. And the shift strategy also needs to be adjusted, right? But power split ratio doesn't have to be adjusted so much. You know, this line is strategy, right? The x-axis is just variable. And lastly, we can extract EV shift strategy, okay? But this can be solved by other methods, not DP, but this is DP results, okay? Again, there's not many points for hybrid mode because you turn the engine on right away, but you have more points for EV mode, okay? And you can see that the strategy doesn't change dramatically. So this is the results, summary of what we discussed so far. So now we can still use the rule-based controller it proposed earlier, right, for hybrids. But we need to adjust engine on off and shift the strategy as a function of theta. So this is adaptive, this must be adaptive, but this may not have to be adaptive. This is a very interesting finding because usually people thought that this will have to be adjusted. People also thought this, this is a good way to adjust it, to change the SOC depletion rate. But one of the most interesting findings here is that shift strategy is very important. And it needs to be adjusted. Depending on the SOC depletion rate. Okay. So in other words, if you want to charge or deplete battery, then you should use engine on off and shift strategy. And then power split blending strategy doesn't really have to be adjusted, but it can focus on optimal engine operation. Because here it's PSR, but if you actually see these points from engine map, engine usually operates in the operating region, efficient region. Okay, now comparison of the proposed DP-based controller and DP. So this is DP-based controller, and we're comparing that with DP. So extracted rule-based controller, and then real DP. And you can see the behavior is quite similar for both theta bar equals 2.6 and theta bar equals 2.38. And we're going to also compare that with instantaneous optimization algorithm. And here's the results. So we are comparing 3 cases. Theta bar equals to 0.667, theta bar equals to 0.381, theta bar equals to 0.1. So charge is sustaining, charge is depleting. And you can see that, again, DP-based controller achieves near optimal fuel economy. But instantaneous optimization has, some gap, performance gap. Okay? And then there's EVCS strategy. This is the worst case controller, because if you do not have any information about the distance, and the simplest way to do this is EV and CS. EV and CS. That's this mode, okay? This is worst case. This is the non-intelligent method, right? So just use the battery as fast as possible and then do CS, okay? And then, and you can see that this gap is significant, right? And notice that the delta, these delta values, performance drop or gain, is more significant for this case compared to these cases. Why is that? Well, I'll finish after this slide, okay? Well, we are using this normalized value, okay? We're normalizing it with respect to DP performance. So DP is always 1. And for each case, we are also dividing it by fuel consumption or fuel economy. Actually, fuel consumption. So fuel consumption. But for this case, where theta bar is high, you have a lot of energy. So fuel consumption is very small. So if you divide it by small value, then the delta will be amplified, right? But in the case of theta bar equal to 1, you already have significant amount of fuel consumption, because you don't have enough battery. So you have to use fuel, even for DP case. So your starting point is different for these cases. So in summary, even though the relative gain is much higher here, the absolute gain can be more significant here, because here fuel consumption is, say, I don't know, 1 liter, but here fuel consumption is only 0.001 liter. So you're looking at, here 50% gain, and then here you're looking at 5% gain. That's what we are talking here. So 5% gain is not small.